This lecture is going to wrap up our look at Chapter 2. We're looking at some basics of measurement and calculation in science, primarily scientific notation, dimensional analysis, and the metric system. So we're going to start with scientific notation. Chances are this is a review of material you've learned in math, so we're going to go through it pretty quickly. But scientific notation allows us to easily express very large and very small numbers without having to write out huge numbers of zeros or a bunch of decimal places. So for example, if we wanted to talk about how far it is from Seattle to New York, it's about 2,852 miles. And we could shorten that number in terms of scientific notation, which just represents how many tens there are within a certain number. So we would shorten this number down to 2.852, and we would show that there are 3 tens represented by writing 10 with an exponent of 3. For some reason, my program, when we converted from PowerPoint to this video program, it dropped all of my exponents, so we'll fix that as we go. But we are representing that there are 3 tens, or 3 times 10 times 10 times 10, which would be 1,000 times this 2.852 miles. Generally speaking, with scientific notation, we have much larger numbers, but this is just a simple example. Some of the basic steps for converting into scientific notation is you count how many spaces there are between the decimal, which always comes after a number between 1 and 9, right? You have a single digit, 1, 2, 3, 4, 5, 6, 7, 8, or 9, and then you will place a decimal for scientific notation. So in this example right here, 304.1, we need to move the decimal over so it's right after this number 3, which means we would have to move it 2 places to the left, which means we would have 2 tens represented in that movement. So by moving the decimal 2 places to the left, we are now creating 10 with an exponent of 2. So 304.1 is the equivalent of 3.041 times 10 to the second power. This works the same way if we're moving in the opposite direction. So if we had a smaller number, 0.03041, it also requires us to put the decimal right after that first non-zero digit, which is a 3 still. And we're moving the decimal over 2 places from right here, over 1, over 2. So again, 2 movements, but because we are requiring this number to get larger, right, we're representing 3.041, which is larger than 0.03. We represent that exponentially by making the exponent negative. So 10 to the negative 2 here. 3.041 times 10 to the negative 2. In science, and in all countries, with the exception of the US, Burma, and Liberia, the metric system is used to measure pretty much everything. And it is used in a variety of ways, but there are kind of what we call base units, or units that are consistently used country to country, science to science, so that it's easy to convert between measurements and it's easy for one person to understand and recognize the measurement that was created by someone or some multiple someones else, right? When we're communicating science and sharing our data, it's really important for us to all be on the same page. So in science, we use a system that has been developed and kind of evolved slightly in the last 50 or so years, called the International System of Measurements. This system was designed by a consortium of scientists in Paris, France, and so it actually came out in French initially, and so in French it was the Système International blah 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 blah, which makes it SI for short, Système International. So the common units or measurements that we will use within the SI system, we use a lot of prefixes, which are so handy and helpful. The prefixes are very similar to scientific notation because they represent units of 10, either 10 bigger, 10 smaller, 100 bigger, 100 smaller, etc. Some of the ones you might be most familiar with are kilo, like in kilometer. Kilo means 1,000 in Greek. We use a lot of Greek roots here. So 1,000 kilo in front of any word, in this case meter, represents 1,000 meters. Centi is another one. Centi means 1/100th. So centi in front of any term, in this case meter, represents 1/100th of a meter. It makes it very easy to convert between numbers because all it does is require the shifting of a decimal place, which is very easy to do. So when we measure anything in science, these are the ones that we will most often use in chemistry, although actually there's one missing here. Volume isn't on there, which I'll add. But the ones we will most often use is mass. The SI unit for mass is kilograms. The SI unit for length is meters. Time is measured in seconds, which is abbreviated S, not SEC, but just S. And temperature is measured in kelvins. We'll talk more about that in a little while, but the abbreviation for kelvins is a capital K. The standard unit of measure for volume is in milliliters. So small m, large L, capital L for liters. As I keep mentioning to you, we use a lot of conversion factors when we're moving from large units to small units, which in the metric system is a breeze. Unfortunately, we often are converting from American measurements into the metric measurements. So that requires us to use a more organized system of conversion, which is called dimensional analysis. And it requires the measurements to be converted a lot of times from one unit to 2 or 3 or 4 other units. And so in order to do that, we need to have some kind of conversion factor or equivalence statement that shows us what the ratio is between the two units that we want to convert between. So a really common example in American measurements are going from inches to foot. And for some reason, again, my formatting is a little kooky here. But 12 inches equals 1 foot. So we can set that up as a fraction where the inches are on the top and the feet are on the bottom. But we can also set that up where feet are on the top and inches are on the bottom. Those ratios are equal to one another. They're just in opposite organizational format, depending on what unit we're starting with and what unit we want to end with. And we'll look at that a little bit more. So when you are using conversion factors, the most important thing you can remember is to show all work. It may seem to you that it's logical or easy or obvious that you used a conversion factor to get from one unit to another, but it is not always as obvious to other people. So you need to make sure that you spell out which conversion factors you used and how you used them. So for example, take a look at this one here. If we want to know how many inches are in 345 feet, we start with their known value, 345 feet. I'm going to rewrite this down here so the fractions are level. We always include units. So we need to use an equivalent statement that allows us to cancel out the feet and get into inches. So the equivalent statement that allows that would require feet to be down here on the bottom and inches to be on the top of this ratio. Just like a fraction, that allows like terms to cancel, so feet and feet cancel. And that allows us to multiply 345 by 12, which gives us 4,140. And now because our unit of inches has been eliminated, or pardon me, our unit of feet has been eliminated, we're now in inches. And we have to look back at our initial measurement, 345. So there were 3 sig figs, which means our final answer needs to have 3 sig figs, which in this case it does, because our trailing 0 is not significant. You could convert this to scientific notation if you wanted to, which is what is shown here. It would be 4.14 times 10 to the 1, 2, 3 inches. This is not correct. I don't know where this came from, so disregard that. If you were going to do it into scientific notation, it would look like this. this answer would be equally acceptable. They're both correct, and they both represent 3 sig figs. This example looks at a large multi-step conversion with units that you're very familiar with. So the problem here is how many seconds are there in 1 year? And again, you can see we started with our known value, 1 year, and then we used all the conversion factors necessary to go from years to seconds. So we went days in a year, that was our first conversion, hours in a day, minutes in an hour, and then seconds in a minute. A lot of people would just do these conversions separately, which is fine, but it takes a lot more time, and it's much easier if you just set it up like this. This is why it's called dimensional analysis, because you are working in a couple, you can see both dimensions, as it were, of this conversion, and it allows you to analyze the whole thing at once. So then we can cancel years, we can cancel days, we can cancel hours, and we can cancel minutes, and we're left in seconds. This gives us an easy way to refer back and make sure we didn't miss anything. So we end up with, let's put our commas in here, 31,536,000 seconds. So because these are all exact numbers, right? Well, that's not really true. This number is not exact. There are not exactly 365 days in 1 year. There are actually 365.25 days in 1 year. So this would be our limiting factor, right? There are exactly 24 hours in 1 day. There are exactly 60 minutes in 1 hour. There are exactly 60 seconds in 1 minute. So none of those figures would limit our significant figures. However, this one would. We only have it in 3 places here, right? We didn't include the entire conversion factor, which means our answer really should be reported to just 3 significant figures. Here we reported this answer in scientific notation, which is fine. If we were to report it in appropriate significant figures, it would be 3.15, right? 3 significant figures times 10 to the 7 seconds. Temperature conversions are one that you probably don't use a whole lot unless you travel to other countries and want to know about the temperature. There are 3 temperature scales. The one that we use here in the US is Fahrenheit, which is completely kooky and has it set up so that 32 degrees is the freezing point and 212 degrees is the boiling point of water. Celsius is the one that is most commonly used in Canada and the majority of Europe, which makes a little bit more sense. 0 is the freezing point of water, and 100 is the boiling point. Kelvin is an entirely different scale, which is used in some physical sciences, particularly physics and astronomy, things like that. But we will not use it much in chemistry beyond just practice of conversions. So the conversion factors that you would use to move within temperature scales are all included here. I would never require you to memorize this, but you should be able to use them. So TC here represents the temperature in Celsius, TK represents the temperature in Kelvin, TF represents the temperature in Fahrenheit. Finally, our last unit of measure that we'll use a lot, and again, this came out a little wonky, so let's fix it, is density. Density is a measure of mass over volume, so how heavy something is compared to how much space it takes up. The most common unit of measure in chemistry is grams per milliliter, so weight per liquid volume. But you will also sometimes see it in grams per cubic centimeter, or sometimes people write it cc. Those are equally valid as well. So at this point, please write down any questions you have seeking clarification or things that came up as you were watching, and write a brief summary, and I will see you in class.